Hello, everyone. Today, I've prepared a video on the topic of materials, Sojay in Korean. It could be a far-fetched story. There's a classic film known for its unexpected twist ending, The Usual Suspects, where Kaiser Sojay, a vengeful mastermind, appears. Of course, I'm not here to talk about that Sojay character today. Instead, I want to delve into the core of materials, Sojay in Korean, which are crucial in terms of substances, components, and equipment. Specifically, I will explore advanced materials. This subject is covered in the book review, A Story on Advanced Materials by Kim Young-gun and Ahn Jin-ho, which was selected as an excellent academic book by the Korea Academy of Science and Technology and the Ministry of Education last year. It's great to hear about Kim Young-gun, a co-author and a professor in the Department of Advanced Materials Engineering at Korea University. He is a member of the Korean Academy of Science and Technology. He holds a PhD in metallurgical engineering from Seoul National University and completed his doctorate in materials engineering at MIT in the United States. He has also worked as a senior researcher at Quantum Corporation in the US and Samsung Electromechanics in Korea. Currently, he is leading the Spin Orbit Materials Research Group at Korea University. As for Ahn Jin-ho, he is a professor in the Department of Advanced Materials Engineering at Hanyang University. He holds a PhD in metallurgical engineering from Seoul National University and completed his doctorate in materials engineering at the University of Texas at Austin. He has worked as a researcher at NEC in Japan and serves as the director of the Extreme Ultraviolet Nanolithography Technology Industry University Cooperation Center. He is also a member of the Korean Academy of Engineering. Indeed, one can view the history of humanity as the history of advances in materials development. In this book, they provide easy-to-understand and detailed introductions to crucial materials in modern society and industry, including semiconductor materials, magnetic materials, carbon materials, composite materials, biomimetic materials, and nanomaterials. In this video, we will divide the content into two parts. First, we will briefly introduce biomimetic materials and carbon materials, and in the next part, we will explain nanomaterials and the current status of materials development in various countries. That's a fascinating story about biomimetic materials. Georges de Mestral, a Swiss engineer, had a moment of inspiration in 1948 while walking through a forest after his dog had been chasing rabbits. When he returned home, he noticed that his clothes were covered in tiny seeds from plants, and these seeds were not easy to remove. Upon closer examination with a magnifying glass, he discovered that the attached object was a seed of a thistle, and it had a hook-like shape. Georges de Mestral used this observation to create a unique fastening tape, which he called Velcro. Velcro has since become widely used in various applications in our daily lives. Just like this, materials created by mimicking the structures of living organisms are called biomimetic materials. Where can we learn about water-repellent, hydrophobic technology? We can learn from the raindrops rolling off the surface of lotus leaves, forming nearly spherical shapes. The surface of lotus leaves has thousands of microscale protrusions, and the contact angle of water droplets is more than 150 degrees, resulting in what's known as superhydrophobicity, where water molecules do not adhere to the surface. Inspired by the nanostructure of lotus leaves, technology has been developed to create semiconductor devices. By arranging tungsten oxide to create small protrusions, they synthesized semiconductors with superhydrophobic surfaces. While lotus leaves are not wetted by water, oil droplets with lower surface tension than water can adhere to the leaf surface. There are indeed hints from nature's flora that guide us in developing innovative technologies. Insects are attracted to carnivorous plants because their elongated, pouch-shaped flower petals contain a liquid filled with digestive enzymes. This liquid serves as a trap to capture and digest prey. Scientists have discovered that the edges of these flower petals have a porous structure, which prevents slipping when dry but becomes slippery when filled with water or nectar. Inspired by this phenomenon, they have successfully created materials that possess surfaces that repel not only water but also oil. They created a porous structure with numerous tiny holes and filled those holes with a special solution that doesn't mix with both water and oil, making the surface slippery. It's described as resembling a sponge soaked in water. The lubricant layer formed on the surface is just a few nanometers thick and has the ability to naturally replenish itself due to the fluidity of the liquid, even if it gets scratched. This property has been utilized to develop a non-stick metal surface technology, which is resistant to corrosion. As not all substances can adhere to it, this technology is expected to have applications in surgical instruments as well, as it naturally repels bacteria and blood. Butterfly wings or peacock feathers exhibit vibrant colors that change depending on the viewing angle. This is due to the surface structure inducing light interference phenomena. The unique nanostructure on the surface causes interference of visible light, resulting in the colorful display. The principle of structural coloration was first elucidated by Sir Isaac Newton, and recently, materials that mimic this principle have emerged. One prominent example is the silver thread used in the 50,000 won bill for anti-counterfeiting purposes, which is made using special ink based on structural coloration. Display technology utilizing structural coloration has also been developed. Muscles possess a remarkable adhesive strength that allows them to withstand turbulent waves. Scientists have studied the adhesive mechanism of muscles by investigating the types of adhesive proteins and amino acid sequences. As a result, they have developed a non-toxic chemical component that mimics the adhesive properties of muscles, known as polydopamine. This substance can be coated on various surfaces, making it applicable as an underwater adhesive and even as a medical adhesive, such as a hemostatic agent. Indeed, adhesive hemostatic agents and blood-free syringes have been developed, which are particularly useful for patients with hemophilia or those taking aspirin. The principle behind these innovations involves a rapid sealing process, where the adhesive on the outer surface of the needle quickly covers and closes the wound the moment the needle is removed. When banana peels are left to decay, the fruit inside turns brown, and the same happens with apples and potatoes when their peels are removed. While humans form scabs when they bleed, insects and plants do not have blood and undergo a browning phenomenon to protect and heal themselves. This process is facilitated by a chemical compound called polyphenol. Polyphenols exhibit a color-changing property, turning black when in contact with oxygen. This characteristic is harnessed in color-changing shampoos. However, traditional shampoos often remove polyphenols along with other impurities using surfactants. To address this issue, adhesive technology inspired by muscles is incorporated into these shampoos, allowing polyphenols to stay on the hair while eliminating unwanted substances effectively. Professor Lee Hae-shin from the Korea Advanced Institute of Science and Technology, KAIST, has developed a shampoo that contains polyphenol compounds with a molecular structure similar to polydopamine. When added to the shampoo, these polyphenols adhere to the hair and do not wash away, but instead, they undergo a color change when exposed to oxygen, resulting in a darkening effect on the hair. Gecko lizards have millions of stiff hairs on their footpads, each about 100 micrometers long and 10 micrometers in diameter. Each of these hairs further divides into hundreds of finer spatula-shaped setae. This intricate structure allows the gecko to exert a strong adhesive force through the phenomenon known as van der Waals forces, when the coarse and fine hairs come into contact with a surface. These forces are named after the Dutch physicist Johannes Diderik van der Waals and represent the attractive forces between nearby objects, which become stronger as the distance between the two objects decreases. Inspired by this phenomenon, scientists have developed adhesive tapes that do not require any adhesive substance. These tapes overcome the drawbacks of traditional tapes, such as causing skin irritation with prolonged use and leaving surface scratches when removed from an object. Indeed, the robotic creation, StickyBot, was inspired by the movement principles of gecko lizards. Spider silk is known to be stronger than steel and more elastic than nylon, surpassing any fiber produced by humans in terms of its remarkable properties. However, mass rearing of spiders is challenging due to their complex behaviors. When placed in close quarters, they tend to fight and cannibalize each other. As a result, scientists have developed methods to produce spider silk by inserting the gene responsible for spider silk protein, fibroin, into the genomes of other organisms such as bacteria and goats. However, artificial spider silk has not fully replicated the exact properties of real spider silk, and continuous research is being conducted to improve its characteristics. During the observation of the silk formation process, scientists discovered that the fibroin, in its liquid state, undergoes a transition from neutral to slightly acidic conditions with an increasing concentration of carbon dioxide as it exits the silk spinning pathway. Although this process is known, the exact mechanism by which it contributes to the strength of spider silk remains yet to be fully understood. It's fascinating to see that materials mimicking spider silk are already being applied in areas such as body armor and industrial cables. These materials not only possess high strength and flexibility but also exhibit high biocompatibility, making them suitable for implants, artificial joints, and surgical sutures. Scientists even anticipate the possibility of using artificial spider silk to create biological tissues like heart muscles or skin. In a previous video about synthetic biology, we introduced Bolt Threads, a U.S. startup that developed artificial spider silk using genetic engineering techniques to produce spider silk proteins within yeast cells. Unlike spiders, silkworms can be mass-reared, making commercialization of silk production feasible. Silkworms are the larvae of the silk moth, which produce liquid silk, silkworm silk, derived from the proteins and amino acids accumulated from eating mulberry leaves. Each silkworm produces silk threads with a length of up to 1.5 kilometers. Indeed, the antimicrobial properties of copper have been utilized since ancient times. Historical records from Egyptian papyri mention the use of copper compounds for disinfection, and in ancient Persia, there was a law stating that drinking water should be stored in copper vessels. Copper is known to release reactive ions upon contact with bacteria, such as coronaviruses. These ions can create scratches on the virus surface, penetrating the virus interior and disrupting essential metal components, such as iron and zinc, which are crucial for protein function and metabolism. Regarding the efficacy of antimicrobial films containing copper, the exact extent of their effectiveness is still uncertain. More research and testing are needed to determine the full potential of copper-infused plastics in antimicrobial applications. The emergence of antibiotic-resistant superbugs due to the overuse of antibiotics and disinfectants has become a concern. As an alternative, researchers have looked to nature for inspiration, studying shark skin and cicada wings. Shark skin is covered with millions of tiny dermal denticles, which disrupt the attachment and clustering of bacteria. This unique texture helps prevent bacterial growth on the skin. Similarly, the wings of some cicada species have sharp, pointed nanostructures that are believed to pierce and destroy bacterial cells upon contact. Researchers have developed materials inspired by these natural designs. For instance, a material called sharklet mimics the texture of shark skin, and another material with silicon surfaces resembling cicada wings has shown antimicrobial properties. In another context, plants perform photosynthesis, a process that converts light energy into oxygen and glucose from carbon dioxide and water. Inspired by this natural process, artificial photosynthesis is a technology that utilizes solar energy to synthesize fuels and chemicals from water and carbon dioxide. These biomimetic approaches hold promise in developing new antimicrobial materials and sustainable energy solutions while taking inspiration from nature's ingenious designs and processes. It is gaining attention as a next-generation technology that contributes to solving energy problems and reducing carbon dioxide. For example, there are oxygen molecules and hydrogen produced by water splitting, and methanol produced by the reaction between hydrogen and carbon dioxide. In photosynthesis, plants use chlorophyll as a catalyst to promote the reaction, and in artificial photosynthesis, photocatalysts are used. There are materials for promoting water splitting and materials for promoting the synthesis of new substances. However, producing clean energy hydrogen through artificial photosynthesis is still less efficient than electrolyzing electricity obtained from solar power. Nevertheless, the technology continues to advance. Carbon materials are the focus this time, following biomimetic materials. In the beginning, the universe contained mostly hydrogen and helium. About 75% of the elements in space are hydrogen, while approximately 25% are helium. However, after the Big Bang, a small amount of other elements was created, and one of them is carbon. Carbon has an atomic number of 6 and an atomic weight of 12. On Earth, nearly 98.93% of carbon exists as carbon-12, and there are trace amounts of carbon isotopes with atomic weights of 13 and 14, which are considered carbon relatives. Carbon-14, with an atomic weight of 14, has an interesting characteristic. It decreases over time, and its half-life is 5,730 years. This property allows scientists to measure its quantity and date ancient fossils. This is known as carbon isotope dating method. Carbon is an incredibly diverse element found in various substances around us, including coal, gasoline, and cells. Depending on how carbon atoms bond together, different forms of carbon exist, such as graphite, diamond, and amorphous carbon. Graphite is soft enough to easily break when rubbed against paper, yet it is one of the most heat-resistant materials, maintaining its strength even when heated to temperatures as high as 2000 degrees Celsius. On the other hand, diamond, another carbon relative, is the hardest natural material known, but it is less heat-resistant compared to graphite. Additionally, there is a synthetic crystalline form of carbon called fullerene, which has a structure similar to graphite but contains hexagonal rings like graphite along with additional pentagonal or heptagonal rings. Fullerenes have various structures beyond C60, Buckminster fullerene, such as C70, C96, and others, where the numbers represent the count of carbon atoms in the molecule. These nanomaterials are actively researched in the field of nanotechnology. Fullerenes possess stable structures, making them capable of withstanding high heat and pressure. Although specific applications are yet to be fully explored, there is potential for their use in semiconductor devices and solar cells. During the synthesis of C60, researchers discovered carbon nanotubes, while observing the byproducts under an electron microscope. Carbon nanotubes are materials where carbon atoms are arranged in a tubular structure, with diameters on the order of nanometers, making them a type of nanomaterial. In 1991, Dr. Sumio Iijima of NEC Fundamental Research Laboratories in Japan discovered multi-walled carbon nanotubes, where several nanotubes are layered, and single-walled carbon nanotubes, which are empty inside. Carbon nanotubes can exhibit both metallic and semiconductor properties depending on the arrangement of carbon atoms. Researchers are exploring the use of carbon nanotubes in transistors, leveraging their electrical properties instead of silicon. Until the mid-2000s, manufacturing costs were high, reaching thousands of dollars per kilogram. However, continuous improvements in the manufacturing process have significantly lowered the costs to the level of a few $100s per kilogram. With the expectation of further price reductions, carbon nanotubes are anticipated to become widely used in everyday life. Graphene refers to a two-dimensional structure where carbon atoms are arranged in a hexagonal lattice in a flat plane. It was named graphene after successfully peeling off a single layer of carbon atoms, thickness of 0.2 nanometers, from graphite, commonly found in pencil leads, using adhesive tape. Graphene exhibits remarkable properties, making it an outstanding material. Its strength is over 100 times higher than steel, and it also possesses flexibility and elasticity. Additionally, its thermal conductivity is more than 10 times higher than copper, and it has excellent electrical conductivity. In recognition of its discovery, the researchers received the Nobel Prize in Physics in 2010. Currently, researchers are exploring various applications for graphene based on its outstanding flexibility and electrical properties. These applications include touchscreens that can be bent or folded, next-generation semiconductor components to replace silicon-based ones, and solar cells, among others. It is said that using graphene filters could turn seawater into drinkable water easily. Water molecules can pass through the graphene, while salt cannot, making it a promising option for desalination. However, cost remains a significant challenge. Currently, efforts are underway to develop a mass production method for large-scale graphene, but achieving flawless and cost-effective production still presents significant obstacles. Plastic, on the other hand, owes its development to a single advertisement that involved a considerable amount of money. In the 19th century, billiards became a popular pastime among the upper class in the United States. At that time, billiard balls were made from ivory, and only 6 balls could be produced from a single elephant tusk. The relentless hunting of elephants for ivory led to the search for an alternative material. In 1863, the American Billiard Ball Company offered a $10,000 reward to anyone who could find a substitute for ivory in making billiard balls, as they sought to put an end to the indiscriminate hunting. John Wesley Hyatt, a printer who saw the advertisement, eventually succeeded in inventing the first synthetic plastic after numerous attempts. The commonly known plastic is mainly composed of polymers, which can be molded into various forms: lightweight, strong, cost-effective, transparent, and can be colored as well. The term polymer comes from poly, meaning many, and mer, meaning one molecular unit. In other words, it refers to a giant molecule formed by repeatedly connecting the same molecular units. Depending on additives, films, coatings, adhesives, and other products can be produced. Polyethylene is the most popular plastic. It is used everywhere, from plastic bags, shampoo bottles, toys to bulletproof vests. High molecular weight polyethylene, with many molecular units, is used to create strong fibers like Kevlar for bulletproof vests and cables. Polyvinyl chloride, the plastic commonly known as PVC, and is used in hardware stores, among other places. It has good resistance to both water and fire, making it suitable for making pipes and raincoats. Polymethyl methacrylate, PMMA, is a transparent plastic that serves as a substitute for glass, addressing the fragility of glass. Acrylic used instead of glass is PMMA. In ice hockey rinks, PMMA is used for transparent barriers to protect the spectators from flying pucks. It is also essential for creating transparent windows in aquariums. Carbon materials are expected to be used as artificial muscles and electromagnetic shielding materials. Carbon nanotubes can be twisted into spiral shapes to create a thread-like structure, similar to a coil spring, allowing for not only contraction and expansion but also rotational movement. Rotational artificial muscles convert electrochemical energy into kinetic energy for motion. By transferring ions to the fibers, the material contracts and exerts force, similar to the way muscles contract. Additionally, there have been developments in artificial muscles that have ion exchange resins coated on their surfaces, enabling them to generate even more powerful forces. These artificial muscles can produce 8.2 watts of force per gram, which is 30 times stronger than human muscles of the same weight. If robots could utilize artificial muscles instead of motors for their movements, they would be able to move more like humans. However, it's worth noting that artificial muscles currently have an energy efficiency only at about 1/5 of human muscles. Further advancements are still needed to improve their efficiency. EMP, electromagnetic pulse, which can disable all electronic devices, is not only a concept seen in movies but also a real-world concern. Among the methods to block electromagnetic waves, there is an approach called electromagnetic absorption, which converts the energy of the electromagnetic pulse into heat to neutralize it. This principle has been utilized by coating electronic devices like smartphones, computers, and cars with conductive metals to shield them from electromagnetic waves. However, this coating process has faced challenges as it adds weight and thickness to the devices. As a result, the development of new electromagnetic shielding materials has become crucial. Composite materials using conductive polymers like polyaniline and single-wall carbon nanotubes have emerged as potential solutions. Plastics have become a versatile material, but at the same time, they have become a looming threat to humanity. They take only 5 seconds to produce, 5 minutes to use, but up to 500 years to decompose. Microplastics are now circulating in the ecosystem, returning to humans through sources like microdust, food, and drink, presenting ecological and health risks. Bioplastic refers to environmentally friendly plastic materials and products that aim to complement or replace traditional plastics produced from fossil fuels. Among them, biodegradable plastics can be broken down by microbial action into water, carbon dioxide, methane, and other biomasses within a year under specific conditions. Biomass-based plastics are made by incorporating a certain amount of raw materials derived from plants, such as sugarcane, corn, or wood straw. While biomass-based plastics may not decompose as quickly as biodegradable plastics, they are considered more eco-friendly compared to traditional petroleum-based plastics, as they result in relatively lower carbon dioxide emissions during the production process. Carbon exists in hundreds of thousands of compounds and plays a vital role in providing energy to all forms of life. No life forms exist without carbon, and atmospheric carbon dioxide is absorbed by plants through photosynthesis. However, with the rapid increase in the use of fossil fuels, there has been a significant rise in atmospheric carbon dioxide, leading to global warming issues. To address this, the concept of net zero emerged, aiming to balance the amount of carbon emissions and carbon absorption, ultimately achieving a net zero carbon footprint. Captured carbon dioxide can be chemically transformed into various useful materials, such as raw materials for chemical products, plastic powders, biofuels, and pharmaceutical manufacturing. All life forms eventually return to carbon. We briefly explored new carbon materials such as fullerene, carbon nanotubes, and graphene. That concludes today's video. Thank you for watching until the end. See you in the next video.